Thank you. I mean, it's always a pleasure to be in Rio and in Brazil. Last time I counted, I've spent more than 7 months in Rio. And I was at the IMPA before the IMPA came here. I was there at the Praça Tiradentes. So that's a long time ago. Now, what I would like to talk about is some problems which are not quite mathematical, where one uses mathematics to try to understand some problems. And at this point, the conclusions are not clear. So I will today speak about something called linear response. Then I shall speak about turbulence, and next thing I will say something about use in biology of some results in statistical mechanics. I mean, this is not so much original work as quoting some work of Jeremy England, which has had quite a bit of interest. Okay, so today I will talk about linear response, and I assume that I have a diffeomorphism and that there is a natural measure associated with this diffeomorphism. This probability measure is obtained by taking Lebesgue measure, normalized Lebesgue measure, on the space on the manifold M, which I assume to be a compact manifold. And I assume that rho alpha is a weak limit when n tends to infinity of f alpha to the power n applied to the Lebesgue measure. Okay, so these measures are called SRB, or natural or physical measure. And at this point, I would like, I mean, this definition is not very precise. One has obtained, in fact, Le Drapier and Young have obtained a characterization of the measures of interest, which is the following, that I will now use terms that I have not yet explained, but they are smooth along unstable directions. There are so-called unstable or expanding manifolds, and the SRB measures are smooth on those manifolds. Or an equivalent definition is that the entropy, the Kolmogorov-Sinai invariant of the measure is equal to the sum of the positive Lyapunov exponents. So, I mean, this is a statement which has not been explained, but to make sure that these SRB measures are well-defined objects. In this lecture, I will use more naturally this definition, and I will not be completely rigorous, but try to indicate the direction of in which one could find a rigorous result. Now, so the notion is that if you have diffeomorphism, or which means a time evolution, there is for this time evolution uncountable family generally of ergodic measures. So that's too many. You would like to say that there is one natural measure associated with this time evolution. And there are a couple of definitions more or less equivalent to the following. You start with the Lebesgue measure, or a smooth measure, and you iterate the time evolution on that, and then take a weak limit, and that would be a natural measure. However, in physics, what you do often is to look how things change when you change a parameter. So the notion would be you start with a diffeomorphism f alpha, which depends on a real parameter, say, and you would like to see how the corresponding measure rho alpha, the corresponding physical measure, changes with alpha. Preferably, it changes differentiably, so you would have the possibility of defining d rho alpha by d alpha and find some expression for that. That means you have a system which is defined by a knob, and you turn a little bit the knob, and the reaction of the system changes, and you see how this, you try to make a linear approximation to this change, and you would like to prove that this derivative exists and compute what it is. That's a physical problem. Now, there are interesting results about that, some positive, some negative, like, for instance, there is no such derivative. You can easily find systems for which this is true. And this means that looking at linear response, the linear part of the response of the system to the change of the dynamics is not a good problem in that case. But there is a little bit of difference between mathematicians and physicists in the sense that the mathematicians like to ask yes or no question, and yes is good and no is equally good. Well, physicists like to find a positive answer to their problem. If they find a negative answer, then this means that this was not the right question that you wanted to ask. Okay, so I claim that there is a formal linear response, namely a formal expression for the derivative of rho alpha by alpha applied to a test function phi and taking the derivative in a certain direction indicated by a vector field x. I will come back to that in detail, and that there is this expression there. And no, there are cases where one knows that this expression converges and gives indeed the derivative. There are cases where this expression diverges and there is no derivative, and in many cases one has no answer. Now, the reason one would like to have an answer is to be able to make a theory of response of a system to certain changes. Now, what I will try to do is to indicate a possible answer. So this is non-rigorous, and the possible answer is that assuming certain genericity conditions that I will not go into right now, assuming the fact that there are stable and unstable tangencies. Now, what does, before defining stable and unstable manifolds, let me look at one system and take this system and let its time evolution do something like this, fold it. Then there is a compression in this direction, which means that the compressing direction will be tangent to the structure, to the asymptotic structure of this thing. So that is what stable, unstable tangencies mean. Now, there is one class of dynamical systems which has been extensively studied, and these are the hyperbolic dynamical systems. For hyperbolic dynamical systems, there is an expanding direction and a contracting direction, and these are never tangent, and the expanding and the contracting direction span the whole set of direction, namely the tangent space to the manifold M. Now, the beauty of the hyperbolic systems, also axiom A in Smill's terminology, is that one has a large number of mathematical results. In particular, the claim that this derivative exists for the SRB measure is proved for the axiom A SRB measures. However, having a chaotic system, a system with in which small errors in initial condition become large for large times, this occurs very often in physics, but hyperbolic systems do not occur very often. So it is a well-known fact that in the space of all diffeomorphisms, there is an open set in the C, 1 plus epsilon topology, which consists of hyperbolic system, but the systems that one finds in physical descriptions, or in the descriptions of physical systems, are usually not like this. They are more like this folding situation here, which is much less well understood. There are some results on which Jacob Alice has worked involving these tendencies, but they are slightly negative results, infinitely many things and things like this. So here one would like to prove a positive result. And the positive result, which one tries to prove, is that there will be a linear response under a condition which is that the unstable dimension is greater than 1. Now, let me make a picture of such an attractor, because this is what the asymptotic measure here, this physical measure in phase space. If the volume is not conserved, this measure is carried by a small set, a set of relatively small dimension, and the sort of thing that one finds is something like this. And if one looks at the cross-section, then this is typically Cantor set. And the Cantor set can have a dimension close to 0 or close to 1. And in the case, the situation, in the case where the transverse measure is close to 0, then this result does not hold. In fact, if one looks at this SRB measure as a function of the parameter alpha, one has a set which is totally discontinuous with all kinds of discontinuities. So this is what one would like to stay away from. And so what I will try to do is to give some argument why, if this stable dimension is greater than 1/2, and I'll explain why 1/2, then this is a different situation. This would be of interest because the stable dimension in general increases when you have larger, when you have more complicated systems in more dimensions. And so it is believable that for many physical systems there is a linear response. In fact, people do measure a linear response, and they don't ask themselves questions about whether it exists or not. But in some cases it definitely does not exist, and in other cases it does. The cases in which the linear response does not exist is the following. If you take a map of the interval 0, 1, x goes to a x 1 minus x, then the behavior, the asymptotic behavior of the system depends very sensitively on A. There are situations where there is an absolutely continuous invariant measure on the interval for this transformation, but this is a very unstable situation. It can certainly not be differentiated. This is a phenomenon that, let's see. That was discovered by Misha Jakobson, and then this led to a lot of results. So you have this. This system is, of course, not a diffeomorphism. It's non-invertible, but it has an interesting feature that if you have an absolutely continuous invariant measure for this thing, then it has a density which tends to have 1 over x minus xi densities. So what happens is you map this interval 0, 1 to itself by something quadratic. This quadratic thing has a maximum, and the image of this maximum, the image of the Lebesgue measure by this map has a 1 over square root of x minus xi plus or minus, depending on the case. And this is certainly a very singular situation. Okay, so the non-differentiability of the physical measure as a function of the parameter seems to be linked to 1 over x singularities for the invariant measure. And to allow you to go to sleep, I will now point out the one thing that might save us, and then I'll go a little bit more into details. So you have these tangencies which are projected in some direction which is roughly expanding, and this is contracting. And the image of this measure, which is smooth along unstable direction, will give 1 over square root singularity. And one can check that this leads to trouble. In fact, this formula, if you put a 1 over square root for in the measure, in the projection of the measure, will lead to a non-convergent expression. What one can hope for is that this 1 over square root singularity will be smeared by an accumulation of stable manifolds that of unstable manifolds that carry a smooth measure. So this means that convolution of this 1 over square root singularity with a measure that is transverse here to the unstable direction will give a superposition of one over square root singularities, which will be smoother and therefore will permit this thing here. As an example, if you start with diffeomorphism on a smooth manifold which preserves the volume, and this may have singularities, it may have tangencies between stable and unstable directions. Nevertheless, the derivative, if there is exponential mixing, this will converge. So one has examples which lead one to think that something like this might be correct. Unfortunately, the number of examples in dimension greater than one that one can analyze is very small. There are, of course, all the hyperbolic systems, but apart from the hyperbolic systems, one has very little control of situations. So one has a lack of examples that one can compare with conjectures or theories. Okay, so let me, the time is moving, and I shall I would like to give a sketch why this formula formally is true. So this is a formal thing, and I will not go into the details of the calculation, which is, apart from that, straightforward. The notion, it says that they are unable to verify the identity of the website, etc. Okay. That's the IMPA that is unable to verify something on my computer. So, write F. Yeah?
You want to project something?
Use this part of the blackboard.
Black part is better.
Okay, very good. So, if we look at F alpha to the power k applied to x, this is the same thing as F0 applied to x plus alpha sum over j equal 0 to k of t f j x f k minus j x of f j x. So let me try to tell you what I'm doing without going into the details of the thing. So I'm taking alpha equal to 0 and look at a small perturbation of the diffeomorphism f sub 0, which I write as f sub 0 of x plus a vector field, which is the derivative of, with respect to the perturbation parameter of the diffeomorphism. So this big X is this perturbation, And then replacing, taking f without index to be f0, I can compute f alpha k of x as such a sum. This is the linear order. This is to first order in alpha. Okay? Then I can look at the function phi of f sub alpha k x and write an expression which is the first order, which is a first order in alpha. It is the f of the diffeomorphism at alpha. And I can transform this expression. Let me try to get the change in rho of phi is equal to the limit when n tends to infinity, 1 over n, sum for j positive, sum for I positive, sum from j equal 1 to n minus I, integral of f j star L dx x of x gradient x phi f I. So this is just rewriting the change of the rho when I have changed the diffeomorphism, when I have replaced the diffeomorphism at 0, at alpha equals 0, to diffeomorphism at a small value of alpha. And then what one will do is take this limit to be divided by n to be the rho to dx. And then one gets a formula which is this thing, except z is replaced to 1. So I make a formal calculation of the response of the system to a change of the diffeomorphism f, a linear response, formally because I make an exchange of orders of limit which is not permissible in general, and I get an answer which is this one when z is equal to 1. So, I mean, without going to the details, this is a sort of, this is a natural sort of formula because it contains linearly the derivative of the diffeomorphism with respect to alpha. and is an expression as an infinite series, which may or may not be convergent. Now, this is the formal expression for this linear response, which may or may not converge, may or may not be correct. Let me now indicate some known results. If I have a hyperbolic diffeomorphism so that one can, at each point of the manifold, or at least at each point of an attractor, find an expanding direction and a contracting direction, and these point in span the whole space, and they depend, these directions depend continuously on where you are, then one can prove that this SRB measure depends not only continuously but differentiably on the diffeomorphism or the parameter alpha, and one proves that the derivative is given by this formula. I mean, this formula, it may or may not make sense, but it is the natural formal response, and if there is a derivative, it's not too astonishing that it's given by this expression. So there is one case at least where one has a linear response, and there is a similar result for flows, but I prefer not to go into flows. Now, how does one make sense of this thing and prove that it converges for z equal 1? Well, decomposing the vector x into the stable and unstable direction, one has a sum for n equals 0 to infinity of zn integral rho alpha dx x stable of x gradient x phi fn alpha, plus the same thing with the unstable direction. And while in the stable direction, the f which is here means that you contract the vector x stable, and therefore this sum morally converges to a limit. In the unstable direction, the vector is expanding, and one does not have something which is visibly convergent. However, one can make an integration by part so that this x gradient is replaced by a divergence of x unstable in the unstable direction of x times phi of f n x So what we have is here a minus sign because of the integration by part of a divergence which makes sense and is a Hölder continuous function in the case of a hyperbolic system times a function phi, which we suppose to be smooth or Hölder. And this is a correlation function. And being a correlation function, it decreases exponentially when n tends to infinity. So this shows that this sum converges. It converges for one part because you have a contracting, a vector in a contracting direction, which is contracted exponentially. And in the other direction, you make an integration by part and appeal to the fact that the correlation functions for hyperbolic systems decrease exponentially at infinity. Okay? So that is, still it requires a proof that the derivative exists, but at least the formal expression of the derivative makes sense in an obvious way that there is exponential contraction of the stable direction and exponential decay of the correlation function corresponding to the unstable direction. Now, if you have a diffeomorphism of a manifold which preserves the volume, then you can make this integration by part for the whole of X times phi of fk fnx integral. And if this system has exponentially decaying correlations, then you again have exponential convergence of this sum. So it seems that we have two situations. Either we have hyperbolicity, or we don't have hyperbolicity, but we have a measure which is absolutely continuous with respect to Lebesgue and invariant under the diffeomorphism. And then you have again linear response and exponential convergence of this sum. So it is not, it seems probable that you can have a situation where the measure is almost the Lebesgue measure, and this I will take to mean that the stable dimension is close to the maximum. So think of the unstable direction carry the measure. The measure is absolutely continuous on the unstable direction, and you have piles of these unstable manifolds. And if the thing almost fills the whole space. This is almost as if you had Lebesgue measure, and then it's not incredible. It's possible to believe that you will have again this linear response. I'm trying to give argument that it's known that if this unstable dimension is small, close to 0, you don't have linear response, you have singularities, and there are examples in the one-dimensional maps of the interval, but it is credible that if the unstable dimension is getting close to 1, or, well, is getting above 1/2, then you may have linear response. Okay, let me try to be a little bit more. Yeah?
Question.
Yeah, sure.
This phi inside the formula, there is a phi inside the gradient, and is it an observable phi? This phi.
Phi? Oh, yeah, this is, so I mean, I'm taking the weak limit because the strong limit will not exist. So I make a weak limit integrating over some observable phi. Now, what happens if you have stable, unstable tangencies? What I think about is the fact that you have folding in phase space. You have still these unstable manifolds, and the measure is absolutely continuous on these unstable manifolds, but they are folded, and there will be a compression in this direction. So, what sense does it make that you have tangency? Now, what I'm doing is contrary to what people do for hyperbolic systems. I'm looking at a given measure. I'm making statements almost everywhere, and almost everywhere you cannot speak of tangencies because the set of tangencies will typically have measure 0, and so what does it mean to have tangency if the set of tangencies has measure 0? I mean, it's all right to speak of one periodic point and of the stable and unstable manifolds of this periodic point. However, for an invariant measure, what sense does it make to speak of stable, unstable tangencies? Well, the point is the following. I want here to appeal to the theory of stable and unstable manifolds of Piecine. And what Piecine showed, well, there is a multiplicative ergodic theorem and the possibility of taking the derivative of f to the power n and seeing applied to some vector x and see how this grows when n tends to infinity. In fact, take the logarithm of that, divide by n. This has a limit which is a Lyapunov exponent. So almost everywhere with respect to an invariant measure, and say an ergodic measure, the growth of f, the derivative of f applied to a vector is exponential, and the exponent is a Lyapunov exponent. So this means that in the tangent space to the manifold, one can look at the growth of tangent vectors almost everywhere with respect to this ergodic measure, and this is well defined. Now, the SRB measures are smooth along unstable directions, and there will be growth of volume in the unstable direction. And transversely to that, there will be compression, but no smoothness. And the thing that one has to think of is more Cantor structure in this direction. Now, so at each point you have tangency, you have exponential growth in the unstable direction, and exponential decrease in the stable direction. Now, what the Pearson theory says is that you can find a manifold which is as smooth as the diffeomorphism, which is tangent to all these stable, all these unstable directions. So almost everywhere with respect to ergodic measure, there is a foliation by stable and unstable manifolds, not just direction in tangent space, but manifolds. Now, one way of proving the smoothness of the stable or unstable manifolds is the following. The tangent is given by a subspace for this gradient f, and what one shows is that the product of gradient f1 times gradient f at the point fx, gradient at the point x, etc. This product of gradients grows exponentially, but the growth, which is given by this logarithm, is very unstable with respect to change of these operators, these tangent operators. However, if you take a series of operators Tn, T1, which is perturbed uniformly, there's no continuous behavior of the Lyapunov exponent with respect to such a perturbation. However, if you perturb, if you make a sequence of perturbations that decay exponentially with n, when n tends to infinity, then you have convergence if the perturbation is sufficiently small. So if you take a stable manifold, this is things that in the distant past were very close to each other. And therefore, if you say, look at the product of tangent maps to the diffeomorphism along this sequence, you will have convergence. So what this means is if you take points which in the distant past were very close together, you will have the same Lyapunov exponent, and these things depend continuously. So one has to work on that more carefully, but this means that in fact the tangent space on a stable manifold depends continuously on where you are, and therefore this is really a manifold. I've defined the tangent manifold without knowing that this is a manifold by the fact that these things were very close together in the distant past, and they form a manifold because the tangent space is depends continuously on where you are. Problem? No. Okay. So the same thing for the stable manifolds. No. The stable manifold do not, the tangent on the stable manifold depends continuously on where you are on the stable manifold. However, it depends only measurably on where you are if you change the place, if you change the stable or unstable manifold. So what you have is in fact that the derivative, not only the first but the second and the nth, the kth derivative in various directions on a given unstable manifold make sense and are continuous on this stable manifold and depend measurably on which manifold you take. Okay? So you have something that depends measurably, but smoothly in the along the surface. So if you look at theorems about measurable functions, you find that measurable functions can be made continuous by dropping a set of small measure. Right? Okay, so you have a measurable family of manifolds which you can consider as elements of some good topological space, locally compact or whatever, depending measurably on something, and on a small, losing a small part of the measure, you can make this dependence continuous. This means that these unstable manifolds, if you take away a small set of these unstable manifolds, form a continuous family. Continuous in the sense that the derivatives, the various order derivatives of this, these unstable manifolds depend continuously on where you are. Now, if you think of a folding situation with stable and unstable tangencies, what will happen is that densely among these unstable manifolds will be things that are little folds. So you have to drop these things to get a continuous family. So you have something which is a compact set of large measure on which you have continuity, with a dense set of things where you don't have continuities. So this means that getting away from a small set, you can say that you have a family of unstable manifolds of which you can control the curvature and things like this. And for the stable manifolds, you can also control the curvature. And therefore, by imposing conditions on derivatives, you make sense of having a family of stable and unstable manifolds which have tangencies. However, this means that you are getting rid of sets of small measure over which you have very little control. Now, I will now try to converge, because going to details will not make much sense. I promised you a non-rigorous outline of a proof that something like this convergence may hold at z equal to 1. So what I want to do is to consider these continuous families of stable and unstable manifolds, dropping a small set, and consider what this fold may contribute to this series. And so what I will do is to do as if I had a continuous family defined everywhere and forget about the small sets which I do not control. And then one can study the integrand. So what one will do is to consider a decomposition in two terms, stable and unstable, like this. The stable part will probably not give any problem. The question will come about the unstable part, which one will try to replace by a divergence, omitting the parts of the manifold M which over which one has no control, and then make calculation of the Hölder coefficient of this divergence. Divergence projected on a direction which is like this. So there is an overall direction which is expanded, and this fold is caught in this direction, and one projects, and the projection will give these 1 over square root singularities, smoothed by the stable direction. And one can formally compute the Hölder coefficient, the Hölder exponent of this projection, and then one finds that there is one factor which makes the thing difficult. I mean, you have a gradient. Okay. This x has derivative which is not a measure, because 1 over square root has a derivative which is no longer a function. It's a distribution which does not make sense as a function. But smoothing it with this thing, one gets a function if the smoothing corresponds to a stable direction which is a stable dimension which is greater than 1/2, fighting this 1 over square root, which is 1/2. So I could give more details, but this is not a proof. This is definitely not a proof. This is an argument that maybe one does have this differentiability. This is of interest in physics because, as I said, in physics, one does look for linear response. And what this thing, if correct, would say is that the greater the stable dimension is, the more chance one has to have linear response. Now, the stable dimension is the sum of the stable dimensions in the various stable. I mean, it's a sum that depends on the total stable dimension, and therefore the greater the space in which one is, the more chance one has that this differentiability will hold. So I will stop at that.
Questions, comments? Yes. Google. So next time will be what day? Monday. And maybe you can say a bit about the next talk. Next Monday.
Right now. Okay, so.
Yeah, no, just a brief.
Yeah. Well, turbulence is something that one sees easily in the bathtub, and even mathematicians use a bathtub, and therefore they are they tend to be interested in this phenomenon and try to give it an explanation. And people, I mean, good mathematicians like Jean Leray and Kolmogorov have been interested sufficiently in this problem to make theories. And they are mathematically beautiful theories that have absolutely nothing to do with each other. Leray looks for singular solutions of Navier-Stokes, while Kolmogorov forgets about Navier-Stokes and makes an analysis which assumes homogeneous turbulence and statistical description of the turbulence. And he finds that this assumption of homogeneity is sufficient together with dimensional analysis to get answer to all kinds of problems. Dimensional analysis is something that is more familiar to physicists than to mathematicians. I mean, physicists work with numbers, real numbers usually, and mathematicians work with real numbers also. And to a mathematician, a real number is either rational or irrational. To a physicist, it makes absolutely no sense. A length is not rational or irrational. There are dimensionless quantities that can be rational or irrational, but a length or a temperature has dimension, and it makes no sense to. Okay, so quantities of interest in physics have a dimension, namely centimeter per second or whatever. And if you have a physical law, you cannot take the exponential of centimeter per second, and if you take a product of centimeter per second by second, then you get centimeter, not something of another dimension. So dimensional analysis is sort of trivial. However, in the case of hydrodynamics, the situation is sufficiently convolved that it makes sense to get answers by dimensional analysis. Now, however, the theory of Kolmogorov has had quite a bit of success. It is used to predict all kinds of things. However, it is based on the fact that the turbulence is homogeneous, that there is a spatially homogeneous description of turbulence, and there is evidence that this is not the case. In fact, there are some exponents which one can measure experimentally and which have a certain value attributed by Kolmogorov, and the values measured are different. So turbulence tends to make clumps which is a phenomenon called intermittency. So there is intermittency in turbulence, and one game that one plays is finding intermittent exponents describing turbulence. So the talk that I'm going to give plays this game with in a way which is slightly different from others, which I find more natural, but I don't want to anticipate on that.